Hello everyone, thank you for tuning in. My name's Zixing, and I will be telling you about encrypting quantum computation efficiently with random circuit samplers. Last year, we saw an experimental demonstration of so-called quantum supremacy by Google, where they performed a task called random circuit sampling using superconducting qubits. They showed that such a task is intractable even for the most badass classical computer with one of the largest memories. Demonstrating the exponential advantage of quantum computers over the classical counterpart has attracted a lot of attention lately. So some of these tasks include boson sampling, Fourier sampling, random circuit sampling with either commuting gates, known as IQP, or non-commuting gates, which is what we will focus on. One catch is that these tasks typically do not require the computation to be doing anything useful. And while there are a few exceptions, the meaningful application of these tasks, in particular to quantum information, have been lacking. And this is where we come in. We expect that future quantum computers will be solving important problems, and therefore there will also be the need to encrypt them. And our proposal here is to use a random circuit sampler to encrypt the output of a universal quantum computer. And our result is that we have an encryption scheme with a potentially exponentially shorter key compared to the others. We are exploiting the quantum data locking effect, which is something that is uniquely quantum and has no classical counterpart. So what is random circuit sampling? Well, you'd have your qubits, and you apply a series of random 2-qubit gates in succession, and the task is to predict the output. For our encryption and decryption purposes, we actually only need Clifford gates, and this is one of the strengths of our schemes, actually. But actually, if we have access to truly random U4 gates, then the circuit depth required to implement the encryption is shorter. So why do we need encryption of this form? Here we're considering a user and server scenario where, one, the user may not know the algorithm implemented by the server. For example, the algorithm could be patented. Or two, there could be a difference in computation power between the user and the server. So for example, the user can only perform Clifford gates and the server can do universal quantum computation. And there's a huge disparity between the resources needed to implement these two classes of gates. So we're thinking about a quantum state ATM type scenario where server spits out a quantum state that is useful. The authorized user can read the output, whereas an unauthorized user, for example, somebody who didn't pay for it, cannot. So why is our method different from the others? An n-qubit quantum state can be encrypted in several different ways. We can use a classical one-time pad that uses an n-bit key. So we measure the output and encrypt it classically. We can do perfect quantum state encryption. This requires a 2n-bit key. So this is the equivalent of a quantum one-time pad. Or we can do an approximate quantum state encryption, requiring an n-bit key, again, approximately n bits. So this requires that at the output, the state is arbitrarily close to the maximally mixed state. However, we anticipate that the computation done by the server will be providing the answer to a meaningful question, and we simply require that here an unauthorized user does not obtain the correct answer. So this is what we do. So here you have your qubits. The server performs the computation, and then at the end of the computation, the server concatenates the encryption circuit And at this stage, the state is handed to the user. So step 1, the server and the user share an unconditionally secure secret key of log k bits. In advance, but not necessarily in secret, the server and the user agree upon a set of k n-qubit random circuits going from 1 to capital K. The server then applies the circuit ck associated with the secret key, so that's the C here. And the authorized user who has the secret key applies ck inverse and measures the output. So ck is applied, and the authorized user applies ck inverse, turning this block into an identity. And now the authorized user can measure the computation correctly. Now, this is our model. We're saying that the quantum computer solves a problem that has potentially m possible solutions, each encoded in psi of x. And these are orthogonal. They each occur with probability p of x. A legitimate user who has access to the key sees the following state. And we can quantify the uncertainty of the measurement by the minimum entropy given by the negative of the log of the maximization of the p of x. This is different from using the Shannon entropy, which is the average entropy. And we use this quantity because we need it later in the security proof. If we know nothing about the output of the computation, which is typical, then p of x is flat and it's equal to 1 over 2 to the n. And here h min is equal to n bits. And this is important. Now, for an unauthorized user who does not know the secret key, her description of the state is as follows. So this summation over x is what the authorized user sees, but for an unauthorized user, this is also averaged over the different encryption unitaries. Here we've added a dummy quantum system X to carry the result of the quantum computation. And now that we have the state, we can do the security proof. So here, our goal is to upper bound the accessible information between an unauthorized user, Eve, and an authorized user whose random variable we denote X. So the accessible information is the maximization over the mutual information given by this expression over here. And Eve's P of elements takes this form, where if we sum over the elements y, you get the identity operator. I don't have time to go over the security proof, but the two essential tools that we're using here are the matrix Chernoff bound and the Maurer tail bound. And both of these are basically saying that if we add up random variables, the probability that they deviate from the mean, i.e. the maximally mixed state, is exponentially suppressed. And I'll simply show you the result. The details of the proof are given in here. So we bound the mutual information to be 2 epsilon n, where epsilon is a security quantifier, which we've chosen to be 10 to the minus 8 in this plot. It is upper bounded provided that the log of the number of encryption unitaries is larger than 1 plus n minus the min entropy plus some terms which are logarithmic in n and 1 over epsilon. So if h min is large, then we need essentially a constant or log amount of key. So this is the number of bits required to lock an n-bit quantum state. This is the quantum one-time pad in black. The purple is the approximate state encryption. And our state here, if the h min is equal to n, then you see that it's essentially flat. But if we know something about the output, then you need a little bit more key. Here, we are stressing that there's potentially an exponential gap between our scheme and the others. So, in conclusion, we have found a meaningful application of random circuits or random circuit sampling to quantum information. We are considering a scenario where a server can perform universal quantum computation and the user is capable of performing fault-tolerant Clifford gates, or at least Clifford gates. We are exploiting the phenomenon of quantum data logging. And here we have an information theoretic proof which suggests that quantum circuits using only Clifford gates can secure a quantum computation using an exponentially shorter key. And thank you for your attention. And I'll take any questions.